Welcome all. This month's webinar is Miguel Cruz is going to talk us through the 10% rule of thumb for estimating rate of spread, which has come from a number of papers, recent papers. Certainly something that could be a useful, quick prediction tool that we're always looking for. So over to you, Miguel. Thanks.
Thanks, Mike, and thanks for the opportunity to present this work that Marty and I have been doing for the last 3 years. Essentially, is a simple rule, a simple approximation of the rate of spread that comes from the wind speed alone. Really, is the rate of spread will be 10% of the wind speed. So what I'm going to do here is describe how we come up with this, how we developed this rule of thumb, and I'll also look into, by doing some evaluation, and for this case we have contributions of Paulo Fernandes, Musa Kilinc, and Angelo Gil. They provide some data sets to evaluate the rule and kind of start looking where it works and where it doesn't work. So it's the limits of application of this rule of thumb. All right, so for those of you that don't know Marty, Marty is a retired Canadian Forest Service fire behavior researcher, and he's one of the persons behind the Canadian Fire Behavior Prediction System, and also the FBAN training and the curriculum developed in Canada. I met Marty about 20 odd years ago in an FBAN course in Canada in the mid-90s, and some years later we started to work together, and we have been working together for more than 20 years. And this is this work presented here today is the last work we did together. So rule of thumb, also called heuristics, is about something that is easily learned and easily applied procedure. Namely, it is not only based on practical experience rather than theory. Tends to be a principle with broad application and not intended to be too or very accurate or reliable for every situation, right? And so it's a bit of a rule of thumb. As you can see, you measure with your thumb. The term has been coined and been traced back to the 17th century, and it's commonly, even now, it's commonly used in different areas. In terms of wildland fire management, there's several rule of thumbs around. There's one here on the left, a paper from the 1937s, from the 30s, and a simple rule of thumb that allowed to estimate the perimeter increase of a fire based on the rate of forest spread of the fire. The more recent rule of thumb, this crossover concept, and some of you that have been in Canada might have come across this. States that if the RH drops below the air temperature as fuels become increasingly dry, fire activity is going to increase. Another similar one to this crossover concept is the 30-30-30 concept, which states that if the air temperature is above 30, RH below 30, and wind speed above 30 kilometers per hour, you can expect some significant fire activity. So these are quite used throughout the world, these 30-30-30, not so much used in Australia. So if you, as FBANs, we really, you probably have felt situations where the urgency of the situation, the real time available, limit the development of a detailed prediction of fire spread. And in such cases, or other cases where there's no FBAN capability in an area or a country, it would be nice to have something, a first approximation of the rate of spread of the fire based on very simple inputs, right? As say here, and this was, I guess, done on us working in after Black Saturday, interviewing a lot of people involved in Victorian fires, where there was a few F-bands at the time, but not really enough for all the fires that were occurring in the landscape. Nonetheless, there was a need to inform the general public and wildland firefighters of the fire potential occurring. But people, different people in different control centers had no idea of what the fire was doing. Right? So that kind of raised us this idea, well, really, it would be nice to have something simple to predict rate of spread. But when you start working on this, it was not something we had planned. We didn't have a project or anything. It was something that just appeared organically, let's say. And back in the early 2000s, Marty and I were doing an evaluation of a crown fire spread model for conifer forests. And we put together a wildfire data set for North American conifers. And a few years later, 2017, Francois Pimon, a researcher in France with INRA, he mentioned that if you do the ratio between the rate of spread and the wind speed for this data set, you obtain an average ratio that's about 0.09, so very close to 10%. Right? Now the question is, how relevant is this ratio? Now also thinking that as wind speed increases and fuel moistures get critically low, there's a sense that wind speed becomes a dominant factor in determining the rate of fire spread. So based on this premise, we start looking to how relevant or how representative is 0.09, so 90%. How relevant is that? And what's the variability around this average number? Because if the variability is quite high, the average number is a bit like the average number of the phone book. The average number, but it's meaningless, right? And also we wanted to explore, so this data set was for North American conifers, how relevant was this number or something similar to other fuel types such as eucalypt forests and shrublands. Right. So for this, we have a few data sets available. So that on top is a paper that Marty and I, where Marty and I put out the wildfire data set. So these wildfires were collected by different people, different case studies. Normally they are significant wildfires that people studied after the fact, and they publish as a report or a paper. For dry eucalypt forests, also when Phil Cheney, Jim Good, and Lockie and Wendy Anderson developed the Vesta model, they also provided a wildfire data set for which they evaluated their model. So we also have a data set for dry eucalypt forests. And similarly, when Wendy Anderson developed her empiric shrubland fire spread model, she also provided a data set of wildfire and shrublands that she used to evaluate her model, but in this case, we're using for checking the relevance of this wind speed rate of spread ratio. So in terms of wildfire data set characteristics, that's what we have here. It's a summary in this table. We have about almost 120 observations across these three fuel types, after that in conifer forests, and then what order in dry eucalypt forests, and similar in shrublands. Open wind speeds between low wind speeds up to 50 in the conifer forests and the shrublands. Very similar in dry eucalypt forests, although there's a few fires with wind speeds up to 95 kilometers per hour. Find that fuel moistures very low from 3, 5 to about 10, a bit higher in the shrublands. And in terms of rate of spread, the 3 data sets give the range of rates of spread between 300 meters per hour to about 10.5 kilometers per hour. So that's the data we have to play with. Note also here that most of these runs, these runs lasted between 1 and 3 hours. So this is the time scale, let's say, that's relevant for the F-band work, where you get observations or get forecasts, hourly forecasts of weather. And normally when you do a run across landscape, that's typically what you're working with hourly predictions, right? So in this graph, what we do is put the open wind speed for all these fires and the rate of spread in the y-axis, the different colors for different fuel types. And an interesting fact is when we regress wind speed into the rate of spread and get here the slope parameters, despite the fact that these fuel types are quite distinct in terms of structure, and as fire propagates, even the energy transfer process are quite distinct, namely eucalypt forests, we tend to have a fair bit of spotting. Despite all these differences, the slope parameters for these curves, different lines, are very similar, right? Conifer forest 0.084, eucalypt forest 0.081, shrublands 0.80, and an overall average of 0.82. So, despite all these differences, the relationship seems to be pretty solid. Now, a value of 0.82 or 8% or 9% is not really easily calculated mentally what would be a rate of spread if you want to apply these functions to predict the rate of spread. So we come up with this 10% rule of thumb, right? So in this case, we are inflating the effect of wind. We are giving about 25% more, 25% more of the effect. But again, we are not interested in something that's too accurate, but something that is easily applied. So we state, all right, let's make a rule of thumb where the rate of spread is 10% of the wind speed, right? Here, very clearly stated, that's the only equation I have for this presentation. Rate of spread of a wildfire can be estimated or approximated as 10% of the open wind, average open wind. And this open wind can come from forecast, from the BOM, or from observations. If it comes from observations, it needs to be average 10-meter average observation. So it's not to be used with a gust winds or something similar, or winds measured at the understory of a forest or a eye level next to a road. No, it's about winds that are accurately measured in the open, following the standards that the Bureau of Meteorology follows. So, as example, if the wind speed is 30 kilometers per hour, the rate of spread is 3 kilometers per hour. Right? Very simple. Now let's look at some of the results. And in this graph, I have the predicted rate of spread in the x-axis, the observed. You have all the data points, the pairs observed and predicted pairs, the line of perfect agreement. That's where we like all the data points to be. But you know there's a lot of uncertainty, chaotic process, so we put a plus or minus 35% envelope. And from previous analysis we did come up with this plus or minus 35% is considered a good prediction. Excuse me. So in this case, what you observe is that for the wildfires that are observed to spread with rates of spread below 2 kilometers per hour, the rule of thumb is really over predicting these spread rates, right? This side we have over prediction, this other side under prediction. But when you look at fires that's spreading faster, due to wind, lower fuel moisture. Most of the data within this plus or minus 35% envelope. That's quite an encouraging result, right? Example of this fire here, a large over prediction. It's a fire spreading with a drought factor of about 6, as example. So some conditions, as you start looking at these major errors, you start seeing, and look at detail, you see landscape was not dry enough, as example for this case. Right, and you start to look about some of the limits of the application of this rule of thumb. Now, looking at some of these areas to understand where the rule of thumb works and where it doesn't work. So here we have 2 types of errors: mean bias error, which is the mean of the residuals in units of fire spread propagation, and in the right we have the error as a percent of the observed rate of spread. And what you see in this graph on the right is that for the high moisture contents, about 10, example, errors tend to be quite high, about higher than 100%. But as the fuel moisture starts decreasing, so does the error decreases. And when the fuel moisture are below 7%, you start seeing errors, average errors below 50%. So that's very encouraging, because these are the conditions that you are more likely, somebody is more likely to be faced with a fire that's spreading faster in the landscape, and more urgent predictions are required. Here, in terms of the bias error, it's a bit confusing also here on the high fuel moistures, not much of a trend, but as you start seeing as the wind speeds, the moisture contents drop again below 7.7, 7.5, you start seeing very low errors. And errors of half a kilometer per hour for this group, 5 to 7.5. And for really low fuel moistures, under prediction errors, so the bias, if it's negative, the under prediction of about half a kilometer per hour. Now, if you think about the magnitude of this error, but the magnitude of the fire spread rates that you observe under this range of conditions, you start thinking that this error is relatively small relative to the rates of spread. And this next graph kind of shows that, where is similar the error distribution as a function of observed rate of fire spread. So in this right graph, if you have fires spreading less than 2 kilometers per hour, you have very high errors, about almost 200%. But as the fires start to really spread fast on the landscape, the errors kind of go to some level of about 40, 50% average error. So for the fast fires, the rule of thumb is predicting the fires with a much smaller error. Here, also again, the average residual, what you observe here is also the error increasing in a negative manner, negative residuals increasing as the rate of spread increases. So just saying that the rule of thumb for these really high rates of spread fires is starting to under-predict an average rate of spread. In these very high rates of spread, is between 7 and 10, in this case only 3 fires, there's a lot of long-range spotting. Spot fires more than 10 kilometers per hour, which might have contributed for this high error. But if you look at these fires spreading between 6 and 7 kilometers per hour, and you look at the error, average bias of about 1.5 kilometers per hour, you start thinking that in relative terms of the rates of spread that you're observing, the error is about 25% of the observed rate of spread, right? Even the bias is increasing, but because also the rates of spread are increasing. The bias is still an average in percentual terms is small compared to the observed rates of spread. In this matrix, I try to kind of summarize these results in a different way. So we have two moisture content situations and two wind speed situations. We have high moisture content, where moisture contents go from 7.5 to 20, and also two wind speed conditions, less than 30 kilometers per hour, what we call the moderate wind speed, and more than 30 kilometers per hour, high wind speeds. And so each box has a lot of little statistics, but if you look at these boxed high moisture content, moderate wind speed, the mean rate of spread for these fires was about 1 kilometer per hour, and the mean absolute error, MAE, absolute error for the predictions was very similar, right? About 1 kilometer per hour as well. Average error for fire spreading under these conditions was about 120%, right? So high errors. And also the bias is positive, so the rule of thumb is over predicting the rates of spread. Similar for the high moisture contents and high wind speeds, average errors close to 100%, 85%, let's say, right? So here, average rates of spread much higher than in this box, and average mean absolute errors still quite high relative to the observed rates of spread. But when you go to the lower boxes, the low moisture content, you start seeing that this average error drops considerably. So for the moderate wind speeds, less than 30 km an hour, errors of about 50% average error, right? And when you look at the average rates of spread, about 2 kilometers per hour, and the average bias, 200 meters per hour, you start seeing that the bias is very small comparatively to the observed rate of spread. So predictions are quite unbiased. And the best results really are coming when you run the rule of thumb to the low moisture contents, high wind speed situation, with not just the average error on about 40%, the lowest we got. And you look at the bias, 150 meters per hour compared to average rates of spread of 4.3 kilometers per hour, you realize the bias is very, very small. So really an unbiased prediction. So it looks like the rule of thumb, despite its simplicity, is predicting best in the conditions where they might, there's more of a need of a rule of thumb. Right? An interesting thing also is that so when you have these papers where you took the wildfire data set, each of these papers, the authors were comparing models that they developed with the wildfire situations. So we had the predictions of models for these different wildfires. And so it's conifer crown fires. In North America, for the eucalypt forest, we have the Vesta model predictions. And for shrubland fuels, we had the Wendy's shrubland fire spread model. And when you put the results in the same kind of matrix we had before, with the high moisture contents and the low moisture content below, what you observe is, we consider high moisture contents, the rates, the rule of thumb here on the gray boxes yield errors that are much higher than the models on the black columns, right? So the errors, absolute error, the bias, and the percent error are about double in this case than the models, in some kinds about 3 times the models. So for high winds, for high moisture contents, and independent of wind speeds, we observe the rule of thumb yielding predictions much a lot larger errors than the models. But when you go back again to the low moisture contents and the moderate or high wind speeds, and you compare the errors of the models with the rule of thumb, you see that the errors are very, very similar. So the rule of thumb for these conditions are yielding errors that are comparable to the models that we normally use to predict fire propagation. Now, for that region that we are most interested, this kind of like the low moisture content, high wind speed, we only have about 24 wildfires. Right? And we're interested then to evaluate the rule of thumb really with other independent data and under these more severe burning conditions. We know the rule of thumb doesn't perform very well if high moisture, the moisture contents are high. So we don't care about those situations anymore. We want to better understand how the rule of thumb predicts in severe burning conditions, right? And there was 2 data sets that were available to do this kind of evaluation. One is from work that Sarah Harris and Musa Kilinc from CFA, back in the day when they were working for the Monash University and working with Delft, they assembled a data set of wildfires in eucalypt forests. And recently, Musa did the evaluation of 5 spread models with that data set. And for that, they had about 180 data points or runs in eucalypt forests that could be used for this evaluation. Then there's also another data set that Paulo Fernandes in Portugal has been developing, called it BONFIRE, which is a global fire behavior data set with prescribed burns, experimental fires, and wildfires throughout the world. And in this particular case, we are only interested in wildfires, and the data set provided 170 data points in conifer forests, shrublands, and eucalypt forests that are independent from the data from Sarah and Musa. Now, because we are only interested in evaluate the rule of thumb for the severe burning conditions, we put some data constraints into the data we will use in the evaluation of rule of thumb, and we consider only wildfires that are spread in moisture contents below 7%, wind speeds above 30 kilometers per hour, drought factors above 9. So we're assuming that the landscape is pretty much homogeneously dry. Run durations, again, interested in fires with a run duration with more than an hour. And also another constraint here, only consider fire runs that are pre-wind change, right? We are not interested in the fact or fire propagation if a wind change passes over the fire to form a large flank into a head fire. That's a different process to which the rule of thumb does not apply. And with this case, we have a data set of about 82 wildfires. And just going to directly to the results. So with data from Sarah and Musa, in the work that Musa in 2012 did, he compared this wildfire data set with predictions from the MacArthur fire spread model and Vesta. And so in this graph, we have the predictions that Musa came up with, and also we have the rule of thumb predictions. And rule of thumb predictions are the darker circles. And in this plot on the right, see the residuals, and what you see is, again, despite the quite severe burning conditions, low fuel moistures, high wind speeds, there's a number of fires that are just not spreading very fast. These observed rates of spread, they are spreading with rates of spread below 2 kilometers per hour. Right? And so for these fires, the rule of thumb is really over predicting the observed rate of spread. But as fires start to spread, and all the fires that spread with a rate of spread of higher than 2 kilometers per hour, we pretty much, the rule of thumb pretty much puts the fires within the plus or minus 35%. Right? So quite a good result for the fast fires. One thing you'll notice here in terms of the other models is that also the white circles, McArthur meter, and Vesta, as the fires started to spread faster, there's a under prediction bias, right? And the fires all below the minus 35% error interval. So very similar results to what we observed in terms of rule of thumb with previous data. There's a question: why are these fires here? Why are these fires not propagating, right? And as you could expect, and note that for these conditions, the models predict much better rates of spread than the rule of thumb, much more accurate. Some of these fires are spreading early in the afternoon, so there could be a case where fuel moistures were not as dry. From overnight fuel moisture recovery, they didn't dry enough to meet the requirements of the very dry fuels, despite some models for fuel moisture saying that the fuels are dry. Could be that case. Could also be some fire suppression effect in reducing the fire size. Maybe the fire was still building up. Or could be maybe some fire atmosphere interactions that could be happening here. We don't really know. But the fact is that some fires that the rule of thumb is, or the fires are spreading slower than what the rule of thumb would predict. Look at the BONFIRE data set. Again, we have 3 fuel types here, but only focusing on the eucalypt forests. And the same trend appears for the observed rates of spread below 2 kilometers per hour. The rule of thumb is under predicting these fires. Largely over predicting. Largely over predicting these fires. But the fire spreading above these 2 kilometers per hour, we are seeing most of the fires within this error band, right? Also, something you notice here in this graph is that in the eucalypt forest is that at a bit of under prediction trend, despite the fact that the data points are pretty much within this plus or minus 35%, but really they are getting biased here, negative bias. And there's a note here that all these fires that you see here, they have some significant long-range spotting, talking about more than 10, 15 kilometers per hour. So these 3 fires here, 2 eucalypt fires and 1 conifer fire, these are Ash Wednesday fires. So if long-range spotting is occurring 10, 15 kilometers per hour at that scale or higher, the rule of thumb is going to under-predict, but still not severely under-predict. In relative terms, the error is still quite acceptable. And I think we found in this evaluation is when initially we put a threshold of 7% for the fuel moisture, where the rule of thumb worked best. Through this evaluation, where we have much more wildfires, we figured out that a 5% moisture content threshold was more applicable to get the best results. So there was more over prediction with 7%, between 7 and 5%, than when fuel moisture are below 5%. Right? There's a number of fires that are severely under-predicted. These are the fires spreading with rates of spread less than 2 kilometers per hour. And you see in the summary graph, we're talking about 200, 300% errors, right, within this class. But the errors, independent of the data set, the eucalypt wildfires or the BONFIRE data set, very similar errors obtained by the rule of thumb. So again, for the fires that matter, the ones spreading faster than 2 kilometers per hour, average errors between 22 and 34%. Another key finding is that this rule of thumb predict the fast fires better than the models themselves. It's not saying that the rule of thumb is something really incredible good. It's just saying it seems that as the wind speeds increase and the fires start to spread faster, it's just that the wind speed explaining most of the variation in the rate of spread. That's all this analysis is saying. Wind speed really becoming the dominant variable in determining the rate of spread. So, summarizing some of the major assumptions and limitations of the rule of thumb, wind speed is either measured or forecast at standard height of 10 meters in the open. So again, it can be bomb forecasts or weather station measurements, but it's about a 10-minute average of wind observations. Rule of thumb works best when the landscape is homogeneously dry, talking about drought factors above 9. And as the drought factors drops below 9, the more it drops, more likely you're going to observe an over-prediction of the rule of thumb. Fine fuels should be critically dry, works better when are they below 5%, below 7%, also acceptable, but can expect a bit more of an over-prediction. And applicable for wildfire spreading conifer forests, eucalypt forests, and shrubland fuel types. Very important here, rule of thumb not valid for grass fires. Grass fires, more open structure, more exposure of the fuels to the wind, you get something, the reduction or the relationship is different, closer to about 20%, but there's a lot of variability. There's not, you don't see a constant value in terms of the effect of wind on the rate of spread. The rule of thumb is applicable to large, longer than 1 hour wildfire runs. So it's not for 15 minutes or 10 minutes or 20-minute wildfire runs now, where there's more changes in wind speed and where the fire is spreading over a smaller area in the landscape, where there's other effects. So the rule of thumb really when you are averaging rates of spread over longer time scales. And also in terms of topography, you talk about large fires. So the rule of thumb is applicable for level to gently undulating topography, or when the large fires run across drainages with alternating upslope and downslope runs. Right. So talking about when you talk about the longer run, you have several upslope and several downslope runs in the path of the fire, and that's where this is applicable. If it's just one upslope run, this will be not appropriate because we will not be counting with slope effect. Right? The rule of thumb also assumes that there are no appreciable barriers to fire growth, and existing ones are easily overcome by spotting. So again, if we are talking about fires with fuel moisture below 5 or below 7% and wind speed above 30 kilometers per hour in eucalypt forests and also shrubland forests, you expect to have a level of spotting distance that's going to overcome discontinuities in fuels of about 500 meters, 1 kilometer, a bit more than 1 kilometer, without the fire slowing down. Let's say. If you get the discontinuity of about 3 or 4 kilometers, you might have a spot fire crossing that, but not enough quantity of spot fires that would ensure that the fire would not slow down. So if the barriers to fire growth are significant, the rule of thumb might be over-predicting because the fire is going to slow down as it goes through the barriers. The spot fire will coalescing, accelerating again, but the rule of thumb is assuming that that barrier would not have been there. The effect of spotting in determining the overall rate of spread is implicit in the rule of thumb. All the wildfires had spotting, and so the spotting is implicit. But from the evaluation, we figured out that if long-range spot fires are occurring, talking about 10 to 15 Ks or longer, it is likely that the rule of thumb is resulting in some under prediction. And last note here, even also the spatial variation in wind speed and uncertainty in the forecasts, not such spatial variation in wind, but also temporal variation if you're talking around several hours. You can expect rates of spread prediction by the rule of thumb to have an error interval of about plus or minus 50% of what will be the observed rate of fire spread. Just kind of finalizing, doing some final slides here. And when you talked about this rule of thumb, really thinking about situations where there was no F-band capability, or when time is of the essence. There's no time to predict fire propagation with our typical methods for the use by F-bands, right? No time available for that. And there are situations where fires are spreading into the wilder urban interface, where we really need to have predictions to inform the public of any potential threats. And so the question you put here is, could a simple rule of thumb, like the one described, provide a better appreciation of fire propagation potential for some recent past tragedies? Wildfire that cause a large number of fatalities, right? And here we just want to show a few cases and also illustrate the uncertainty that can exist to wind speed when you talk about fire propagating over large distances. First case here is the Tubbs Fire, 2017 in Northern California. 22 people were killed in this fire in and around the town of Santa Rosa. Again, here the fire was detected at 9:45. Very high wind speeds in the areas between 32 and 70 kilometers per hour. So we start to see here quite a range in wind speeds. And this has to do where you are measuring wind speeds. So these are measured wind speeds on the area of the fire, and there are measurements in ridge tops, there are measurements in valley bottoms. So there's quite a range in wind speed information that existed. But the fire starts at 9:45 p.m. So quite late in the evening. The fire impacted the wilder urban interface of the area of Santa Rosa and nearby about 3 hours after ignition. Nonetheless, evacuation orders for Santa Rosa were only given 2 hours after the start of the fire. So 2 hours was lost here in terms of advised population of the threat from the wildfire that could have been maybe if you have an early and easy prediction could have informed some of these evacuation orders. For this case, we have rates of spread between 3 and 5.2, so these are observed rates of spread from the fire, and the rule of thumb predicting from these wind speeds 3 to 7 kilometers per hour. So the rule of thumb predicting the higher rates of spread, but you can see the observations within the envelope of the predictions given this range in wind speed. Another case, a campfire, and you might come across this in Netflix as a documentary, Fire in Paradise. Very similar weather conditions. In this case, the fire started early in the morning, 6:33, quite early. So again, a situation, a time of the day where you might expect not to have the F-band capability in place to conduct simulations of fire propagation, given that there's no other fires in the landscape. For this case, again, quite a range in wind speeds. Again, valley bottom measurements, ridge top measurements, rule of thumb predictions, 2.1 to 6.2 kilometers, and rates of spread within that envelope, 4 to 4.8. As you can see here, there's a fair bit of uncertainty. The more you measure things, the more uncertainty you have. So it's not a simple process to derive a prediction from if you have variable wind speeds, but it really gets a sense within this envelope you are obtaining the rates of spread observed. So again, a good fit of the rule of thumb, we believed. And again, a case where early morning fire detected, there's people on site, there's people aware of the fire, but there's no simulations to inform of the impending danger to the town of Paradise, which impact town about 1 hour and a half after the start of the fire. Another case, the Mackey fire, also in 2018. Very quick fire. It starts middle of afternoon at 4:40 p.m. You reach the Wildland urban interface within an hour. There were no warnings to the population in this case, but wind speeds vary between 32 and 56 kilometers per hour. So the rule of thumb predicts something between 3 and 6 kilometers per hour, and overall rate of spread was about 2.6 kilometers per hour. So in this case, the rule of thumb, based on the measurements of wind speed, really somehow over-predicting the observed rates of spread, but still a rule of thumb prediction could be useful, in our case, could be useful for warning the population of the impending danger. I tried to use the rule of thumb last fire season, and I found that besides the fact of this when time is of the essence simulation situation, let's say, there's other times where the rule of thumb can be useful. And for one, I was using it when there was a lot of uncertainty in some of the inputs. And I was using it to kind of check. If I was using Vesta and there was some high fuel hazard conditions, and I was getting a very high rate of predictions, and I was using the rule of thumb to check the realism of the predictions. So if you are within that envelope of the high fire spread potential, high wind speeds, high or low moisture contents, even when you use the models, you can check the realism of the predictions if there's a lot of uncertainty to the inputs in terms of fuels situation. So another application of the rule of thumb. There's some open questions. When you look at all this data, why are some of these wildfires showing relatively slow rates of spread under these very dry fuels and high wind speeds? We don't really know. And maybe with the data from last few years, very detailed case study documentation from last fire season, you might get a good grasp of what was happening in some of these fires that might explain somewhat observed in our fires. And also another question, really, why is a simple wind multiplier explaining most of the variability in rate of fire spread and the low moisture content, independent of fuel types, independent of fuel loads, topography, and also some possible fire atmosphere interactions? So that's open questions that we don't have answers, really. We were really, the more we look into the rule of thumb, the more we evaluate the rule of thumb, the more surprised we were how reliable it was explaining the rate of spread. We really, when you start doing the analysis, we really didn't expect to perform so well in that low fuel moisture, high wind speed conditions. So again, it's not so much a rule of thumb value, it's that really, it's about things that the wind speed really dominant things when fires are going. Some details, further details on these studies we are given in these two papers. They, I think, was sent for some FPN network. You can email me or Marty for them as well, or find them in ResearchGate. So a lot of the content, namely the evaluation, some of these significant fires, are detailed in the second paper that we published this year or last year. So if you're curious about that, you can find that information there. And also, we also put some small papers, some summaries of these larger papers available. There's a PowerPoint page from last year, or 2 years ago now, that you can download from CSIRO website. And also Wildfire magazine, we published a very similar piece on the rule of thumb. And I think next month or so, there's also another piece in Wildfire magazine coming out on the evaluation of the rule of thumb. So just a couple of pages really boiling down to some of those important facts. And for people that are not, have no time to read the full paper, let's say. And thanks very much for your attention, for the long presentation. Further questions, that's my email there and Marty's email. And we will be happy to answer any of your questions, not just now, but if you have something you want to come across later, just let us know. I'll be happy to answer some questions. Mike?
Thanks, Miguel. That was very interesting. Does anybody have a question? John Bally?
Thanks. Thanks very much. Look, fantastic presentation, Miguel. Thank you very much. I've got two questions. One of them is when you look at the distribution of errors, there is a bit of a tendency to, with the 10% rule, to over-predict at very low wind speeds and under-predict at high wind speeds. And you talked about some of the reasons why that might be happening, but is another possibility that in most of the models, the wind is included as a power rule, so it's not power one, it's power a bit more than one. So that, a fundamental reason why you're getting that pattern of error. That's my first question, and I'll ask the second one. You can answer them both if you don't mind. The second one is it's remarkably good sort of truth testing guidance for the head rate of spread. Did you look at all at the lateral spread or fire width? Thank you.
Hey, John, yeah, so first one, in terms of the wind speed, some of the errors, the model errors were about the power rule, but when the errors are relative to rule of thumb predictions, that's not related to the power rule, because wind speed is just 10%. The second question, and I guess, yes, some of the under prediction with the rule of thumb seems to be with fires with very well authenticated, very long spotting distances. So kind of take that as a good explanation. For the other range, for the low wind speed, that's probably where might be the case where the wind factor, wind effect on the rate of spread is not well described, but either by the rule of thumb or our rule. The second question, kind of forgot now. What was that?
The work that you've done is really concentrated on the head rate of spread, or the rate of spread of the head fire. Did you look at all at any? Are you able to say anything from a simple rule like this about the lateral spread or the development of the width of the fire?
All right, yes, so the fire size. Yes, in fact, when we evaluated, when you evaluated the rule of thumb against the data, particularly for us in Southern Australia, so we moved the entire data set, there was a trend in the over-prediction relationship with size of the fire. We're talking about fires that in width are about 800, 1 kilometer, 1.5 kilometer width. But there was some of that over-prediction was related to those fires that were smaller than others. They were 2-3 kilometer with flame fronts, right? But that's in that respect. There was we could find for some of those fires, over-prediction effect was related to the fire size. In terms of flame propagation, no, this would not is not something we looked at. Also, we didn't get shape information on the fires to look into that. You could expect in complex topography with some of that upslope runs throwing more spot fires, and you certainly see that in some of the line scans. A lot of spot fires on the side of the fires as well, not just the head of the fire, but on the side of the fires. And those spot fires are really making the overall fire wider than what you'd expect if that spot fire activity was not occurring to the side. So, but now we don't have any information from the data sets we had to look into the rule of thumb wind effect on fire width, let's say, or the relationship between the length and the width of the fire.
Miguel, there's a question about why you needed to exclude the post-frontal spread events.
Yeah, that's a really good question. I didn't include that because that it requires a fair bit of detail. For once, the processes post-frontal, you have air mass normally bringing colder air. So normally, if you use the weather to predict the fuel moisture, you have fuel moisture much higher, right? But there's also, as we observed some of the case studies that have been made in the past, as the wind change hits the flank of the fire, there's a lot of spotting. And as the plume is cut by this wedge and cuts the energy source to the plume, there's a lot of spotting going to the new direction, to the flank. And so it's a totally different process than this, than what we're trying to describe with this rule of thumb, right? So we didn't thought this would be appropriate. There's a lot of more variability in terms of rates of spread or the overall fire growth after 1 hour, after a wind change, than what we observe with this wind-driven fire propagation. So, yeah, we will not go to the point to say that this is applicable to that situation of a wind change. Right? That's the case where we limit. That's why we limit our analysis and prescribe the application of rule of thumb to the pre-frontal change situation.
Thanks. And Lockie's asked that, given you're suggesting that the 10% rule could work quite well after 2 kilometres an hour, do you have any guidance around how long that might take from the fire start to when you should be able to use the rule? sort of allowing for that acceleration of the fire.
Yeah, no, not really. See some fires that are really in certain conditions. Some of these major fires, name some of these case studies from North America and Europe. Within less than 30 minutes, those fires were ripping through the landscape, right? Similarly, some of the fires from Black Saturday, they were Ash Wednesday. They are really going fast right after the start. So I guess it's about also maybe the landscape the fire is going, and where it can build up quickly to a steady state. It's difficult to define sometimes. You look at some of the case study data, and even it seems that the fires, even hours after ignition, even they are spreading faster, it seems that they are still increasing the rates of spread. So not really have a rule of thumb. One thing I guess FBANs can do is look at the radar signal, and if you see these plumes and they are really intense, then it might be the case where the rule of thumb, you can start applying the rule of thumb. But so I don't have any. Seems in some cases almost you can apply the rule of thumb just half an hour or within an hour of fire starting. In other cases you might need some more time. I guess it's up to the FBAN to have a good feel of what's happening, and we did see experience make those calls.
Thanks, Miguel. Are there any other questions? That sounds like it then. Thanks, Miguel. And hang on, there's one more. Just thanks, great presentation. And I concur with that. I think there's quite a bit in there that we can have a look at for those, particularly those initial warnings that we regularly get asked to do something quick and dirty. It's good to have something to do that with. And I'm sure you'd be keen to get feedback on anyone who tries to use it and how they felt it went. So that'd be great.
Yeah, that's right. I know some people that used it in the last fire season. It was a good season to use this. A bit of people used. I used a few times. I didn't get very good results. I get some severe over predictions. Lawrence put me in the same bin. But yeah, so it's not as simple as it comes from this presentation. I must tell you, there's you need to really read the landscape and conditions, and look at some of those signs to know when it really is applicable.
Okay, thanks for that. Thank you for listening, and there'll be an email out hopefully in a week or so advising of the next webinar. Thank you very much.
Thanks, Mike. Thanks, everyone.